Let's now talk about the chemical bonds. So chemical bond is what makes the molecule, right? If we have one atom by itself, it's an atom. If I connect two or more atoms together, then it's going to become a molecule. We have two common types of chemical bonds. So number one is going to be the covalent bond. And the covalent bond is going to be, let me put it here. So covalent bond is going to be between non-metals. For example, a bond between two oxygens, a bond between chlorine and a nitrogen, and etc. This right here is a covalent bond. The covalent bond is formed when two nonmetals share electrons together. Let's say if I have two hydrogens sharing two electrons together, which we can also represent with a line, that's a covalent bond. And this is the H2 molecule. We then also have the ionic compounds, and these are made by the ionic bonds. And so this is simply going to be, if I combine two ions together, one positive, one negatively charged, they're just going to stay together. They will stick together because of the electrostatic interactions, and that's going to be an ionic compound. For example, the sodium chloride, the table salt, is an ionic compound because these two ions, a cation and an anion, stick together because of the electrostatic interaction. All right, so ionic bonds again is going to be between a metal and a non-metal element, and this is because the metals do not like the electrons and they become cations, remember, and the non-metals become anion, and that's how they're going to make the ionic compounds. And then on the other hand, the covalent compound is going to be between non-metals, so elements who have approximately the same affinity for the electrons, and when they make a bond, they're simply going to share the electrons together. For example, again, two oxygens bound together, that's a... Now let's talk about naming the ions. So we'll first talk about generally naming the ions, and this is simply because when it's a cation, when it's a metal, you simply just name it as it is, right? So if it's the element aluminum, it's called just aluminum. If it's a calcium, for example, calcium 2 plus, then it's a calcium. If sometimes there is going to be elements that have two charges, for example, you can have an iron that is 2 plus and you can have an iron that is 3 plus, then the one with a higher charge has a suffix "-ic", so that's going to be the ferric ion, and this is going to be the smaller charge, that's the ferrous ion, right? And sometimes the charge is also represented by Roman numbers. So if I put 2 here or 3 here, then this is going to refer to the charge, and that's how eventually we're going to get the entire name of the compound. So with this said, remember we have type 1 and type 2 cations. Type 1 are the ones that always have the same charge, and this is largely going to be based on the group number in the periodic table. So if it's group 1 and 2, remember these are the good ones. These are the ones that always have the same charge. Any metal in group 1 is going to be positively charged, +1. Any metal in group 2 is going to be +2. The type 2 metals are going to be the ones that they have the charge varying. Sometimes it can be +2, +3, +1, and etc. Now let's continue. So again, this is the iron, depending on the charge, and thin. Okay, so thin can also be +2, or it can be +4. So here again, we're putting in the parentheses. And now the negative ones, the anions, have the ending of the "-ide". And it's important to mention that these are going to be the monoatomic, right? So we're largely talking about here the monoatomic anions. What does the monoatomic anion mean? So monoatomic means that it consists of the same element. For example, chloride bromide, O2-, that's an oxide, S2-, that's a sulfide, and etc. They all have the ending of "ide" because these are monoatomic ions. So you may wonder what is not a monoatomic ion, and these are going to be the polyatomic ions. For example, SO4, 2-, that's a sulfate. SO4, 3-, that's a sulfite, etc. So these are not monoatomic because they consist of two different elements. And so these rules that we are learning here, they're going to be helpful, but the best approach for you is going to memorize all the names of the ions, and this is also going to be tested in the quiz. And this is from the textbook. Look up in chapter 2 the table of the common ions and just memorize all of them. And as you do more practice, you will see that you're going to remember these names of the ions, but this is just going over all the rules of how we name these ions. So these are again, so examples of the ide. We can have sulfide, chloride, and etc. And then the polyatomic ion or oxyanions are going to be the ones that contain an oxygen, and so these are going to be combination of two elements. There is no really rule as to remember the ending, but the ones that are the most common ones, and this is just largely is going to be you remembering them, have the ending of 8, right? So for example, this is the sulfate. Sulf is the sulfur, 8, that's the most common. If it was SO3, 2-, then this will be sulfite. So the ending is going to be the ide. NO3 is the most common oxyion of the nitrogen, so that's -1. Then this is going to be the nitrate ion. Example, so this will be the, and now the ones that have one oxygen less than the most common ion, these are going to have the ending of ide. So for example, here sulfite, chloride, and again these are the ones that have one less oxygen than the most common, and now they have the ending of ide. Next we are going to have the ones that have even less oxygens than these ones, and now these are going to have the prefix hypo, and if it's the one that has more oxygens than the most common, then these are going to be called per. For example, perchlorate, right? Chlorate is the most common, and if it now becomes ClO4 minus one more oxygen, then it becomes perchlorate. ClO minus, that's going to be hypochlorite because this is called a chloride, and if you have even less oxygen than that, then that's a hypochlorite. If it's more than the most common, that's going to be with a prefix per, so perchlorate, for example, right? So here we can see we have the perchlorate and we have the hypochlorite. So let's keep this slide here for a second. Go ahead and take your periodic tables and try to fill out these by putting the names according to the rules that we have just talked about. Okay, so the first one is the calcium, and because calcium is in group 2, it's going to be Ca2+. Next you have the symbol here, so this is the aluminum 3+, but remember for the metals there is no ending or anything changing, so this is going to be simply aluminum. Bromide, so the ending is ide, it's a monoatomic ion and it's going to be -1. This right here is the most common oxy ion of the nitrogen, so that's nitrate, and also we have the sulfate, which we talked about earlier. Now let's talk about writing the chemical formula of the compounds. So The first thing, the most important thing that you need to remember when you're writing formula of the compound is that eventually it needs to be charge free. Your formula needs to be such that it is charge free. So for example, here we have the zinc and the sulfate ion. So that's the zinc sulfate. And because the zinc is 2 plus and the sulfate, so this is 2 plus and this is 2 minus, together it makes a 0. So there's no charge. And this is the zinc sulfate. This you will call barium chloride. And now we'll get to writing the chemical formulas again, but let's go based on the slides for now. So a few important things that you need to remember when you're looking at the formula. So the formula represents one molecule, right? So this whole thing right here is telling you that you have one molecule of this. In one molecule of this subscript here tells you that you have 3 bariums in this formula. This formula represents 3 bariums. It also means that if it's in the parentheses right here, this is the phosphate ion. Phosphate ion, and that's the formula of the phosphate ion. It's PO4 3 minus. And if you have the 2 outside of the parentheses, it means you have 2 of these ions together with 3 barium ions, and the barium is in group 2, and that's plus 6. Each barium has a positively charged plus 2 charge, and if you have 3 barium ions, then that's plus 6. If I have 2 phosphate ions, that's negative 6. So together the charges make it 0. The compound overall is charge free. Subscripts, again, these subscripts tell you how many of each species you have in the molecule. Right, so 3 atoms and 2 of the phosphate ions. So in each of these ions, there is 1 phosphorus, and if we have 2 phosphate ions, then I have 2 phosphorus atoms. And what do you think, how many oxygen atoms we have here? So we have 2 PO4 ions, and in each phosphate ion we have 4 oxygens, right? So for that you need to multiply these two, and that will mean that you have 8 atoms of oxygen in this formula. Now the coefficient is a number that is placed in front of the formula. So if we put the number before the formula, that just means that I have 3 molecules of this compound. So for example, if it's put 3 here, then if I want to know how many barium atoms I have, or ions, then I'm going to multiply 3 times 3 here. So that will be 9. If I want to know how many phosphorus I have here, so it's going to be 2 times the phosphorus and then times 3, so it's going to be 6. And then for the oxygen, I need to multiply everything, the coefficient, the subscript here, and then also the number of the ions. Okay, and so that's going to be 24 atoms of oxygen. Now let's do this quick practice. So for example, how many atoms do we have in this molecule? So NH3 is called ammonia, by the way, so try to remember this. So here's the coefficient. We have 2 in front of it, and that means we have 2 nitrogens, and I need to multiply. So 2 times this, I have 6 hydrogens. And here I'll have 8 sodiums, right? So I'm then gonna multiply 4 times 1 for the carbon, and then for the oxygen it's gonna be 4 times 3, so that's 12. 2 mercury atoms, 2 nitrogen atoms, and 6 oxygen atoms, because I'm multiplying these together. Okay, so take some time, try to do this one now. And here again, the coefficient, you need to multiply this. and it needs to be multiplied by this, which is then multiplied by everything in the ion according to how many atoms you have in that ion. So 15, 10, and we have 40 atoms of oxygen in this representation, right? So this is magnesium phosphate, but if I have 5 magnesium phosphates, then everything is going to be multiplied by 5, and this is how many atoms I have in this given representation. Now, let's continue this. Let's continue naming the compounds. So we're gonna first start with the ionic compounds and then the covalent compounds. So binary compounds, it simply means that we have at least 2 types of elements. So the ionic compounds are going to be easier. If it's type 1, then the cation is always going to have the same charge, and that's always just going to be the name as it's in the periodic table. For example, sodium, potassium, lithium, barium, magnesium, calcium, and etc. So everything in group 1 and 2, and then plus also the aluminum, have the similar behavior. And then if it's a monoatomic ion, you're just ending the "ide," right? So you can have sodium chloride, and etc. So take again a few seconds here, a few minutes, try to name these compounds. Okay, so we have potassium chloride, remember the endings, we have magnesium bromide, and we have calcium oxide. So again, pay attention, number of the metals is not changing. We're only changing the endings to "ide" of all the monoatomic ions. Now type 2, these are going to be the metals that they change their charges. So one example was the iron. We also have copper, and for each we have the tin, and for each you need to go based on the charge. So here you can see chromium, manganese, iron, cobalt, copper. These are the ones that change the charges, right? So this is type 2. Group 1 and 2, this should be the easiest for you because they always keep the charge. Aluminum, gallium, zinc, silver, cadmium, these are also the good ones. And these are the monoatomic. Let's see how we name them, right? So for example, I have this compound and I need to name it. Well, I gotta start from somewhere. I don't really want to start from the copper because the copper is type 2. It has 2 charges. It can be +1, but it can also be +2. So therefore, I'll try to start with the Br because Br is a monoatomic ion and a halogen, and we know that these are always going to be -1. So if this is -1, then my molecule has to be charge free, then this obviously has to be +1 so that together they make 0. And so if the charge of the copper is 1, then it's going to be copperous bromide, or we can also say copper in parentheses 2, in 1, I'm sorry, in parentheses 1, Roman 1, and then bromide. Same for the iron, it can be +2 or +3. So what do you think? Is it +2 or is it +3? And again, that you get from this one. So the monoatomic ion of the sulfur is always -2. And if this is -2, this also has to be -2 as well. And that's why this is the ferrous sulfide or ferrum 2 sulfide. All right, so lead, one important thing again, remember oxygen is the monoatomic ion of the oxygen is -2. So if one oxygen is -2 and you have 2 oxygens, you need to multiply these two together. So overall, they're bringing a charge of -4. And that's why this is going to be, the lead here is going to be +4. Right, so copper 1, iron 2, lead 4, oxide. So again, to a little bit of a summary of this, whenever you have type 2 metal, go based on the counter ion. Look at what you have. If it's a halogen, meaning group 7, that's chlorine, fluorine, bromine, iodine, then go based on that, knowing that it's -1. And if it's sulfur and oxygen, etc., again, the charge of the metal is supposed to be according to the charge of that non-metal. Now, a few examples of polyatomic ions. So one thing that we need to mention here, the OH is a common ion that you need to recognize. OH negative, -1, that's charge actually, it belongs to the oxygen. It's called the hydroxide ion. And this is a very important ion because this makes the basis in inorganic, in general chemistry. So again, take a few seconds here, minutes, look up the name of the ions. If you already remember them, if you learn them, that's great. So that's the nitrate ion, this right here. Look it up, look up this one as well. So this is the NH4. This is called ammonium. So don't confuse this with the NH3. NH3 is the ammonia, so it has no charge. NH4 plus is the ammonium ion, and this is easier, so that's the sulfate, and that's the nitrate ion. So how do you name them? Sodium is a type 1, it's always +1, so it just stays as it is. It's sodium hydroxide. Group 2 stays the same, it's +2, so this is magnesium nitrate. NH4, that's going to be ammonium sulfate. All right, so this will be the names for these ones. And so here's the table that is from your textbook. You need to remember the names of all these ions and do not postpone it because you're going to need them. You will need them in this chapter, in the next chapter, from chapter 3 to all the way to the finishing General Chemistry 1 and also in General Chemistry 2, rather than learning all the rules and applying to naming any chemical. Just learn the names of the ions here, but of course keep the core understanding of how that works also. So sometimes in some cases you may actually need to apply these principles. To work out the formula of an ion. Okay, so I'll skip this slide. This explains how to make a formula, and again, so the important thing that you need to remember here is that is the charge. Overall, the charge needs to be 0. For example, if I have sodium Cl, then it's plus, it's negative. So it's 1, 1 together, they make 0, that is correct. Now, for example, you are asked to draw the formula of magnesium nitrate. So what do? You write down the ions. So you have magnesium, that is 2 plus, and you know the nitrate, that is NO3 -1. Now if you put them together, magnesium, NO3, this is 2 plus and this is -1. You need to now have 2 of these ions to make it 2 plus, to make it overall charge free. So your formula is going to be magnesium NO3 in parentheses 2 times, because again this is +2 and this is -1. So why do we put the parentheses? Just to emphasize, to show that these 2 refers to the nitrogen and oxygen, everything that is part of the nitrate ion. If it was a simpler example, so let's say if you were to draw the formula of magnesium chloride instead of the sodium chloride, then you would put Cl and just 2 here, no parentheses. Because if it's monoatomic, then you don't need to put parentheses, it just belongs to the chlorine. Suppose you need to do, let's say, aluminum sulfate. So what's the formula of the sulfate ion? You have SO4 and it's 2 minus. Now this one is a little trickier, right? So because it's not simply saying that I need 2 or 3 of this because I have +3 and 2 minus. It's not so easy to make them 0. So in this case, what do? You place them next to each other. Let me move over here. So you place them next to each other. And you cross down these numbers to the opposite element. So 2 is going here, 3 is going here. What it gives me is aluminum, 2, SO4, 3. So I need 2 aluminum ions, and I need 3 sulfate ions to make it 0 overall. And why is it? Because look at it this way. So it's 3 plus, this is 2 minus. 2 aluminums, each 3 plus, that's +6. 3 sulfate ions, each -2, that's -6. So together, these two make a 0. And this is what is necessary to write the correct chemical formula. Remember, the objective is to make it overall 0 at the end. There is a lot of these practices in that you can do. So please refer to this. These are in the folder that you can find on Blackboard. I guess I'll play this video and see what example is there. I don't know if you'll be able to hear the audio or not.
Compound, we first select a cation and an anion. Some possible cations are shown here in blue, and some possible anions are shown here in red. Note that the anion might be an oxoanion or other polyatomic anion. Suppose we choose the sodium ion with a +1 ionic charge as the cation and a phosphate ion with a -3 ionic charge as the anion. What is the correct empirical formula for sodium phosphate? Now we can select the number of cations and anions we want to use to build the simplest formula for sodium phosphate. If we select one cation and one anion, we note that the sum of the charges is -2, so the formula is not constructed properly. We must obtain an overall charge of 0 to have a correct empirical formula. If we add another sodium ion so that there are 2 cations and 1 anion, we note that the sum of the charges is -1. Therefore, the formula is not constructed properly. We must obtain an overall charge of 0 to have a correct empirical formula. If we add one more sodium ion for a total of 3 sodium ions, we obtain charge balance and a correct empirical formula for sodium phosphate. To work out the formula of an ionic compound, we charge balance.
So in case you weren't able to hear the video, the audio, here's what was explained is, so if you have sodium and phosphate, suppose you need to write the formula of the sodium phosphate. So just like as we did here, so you're gonna need 3 sodium ions and 1 phosphate, because phosphate is -3, and overall they're going to make a charge-free formula. Let's do one more. So suppose you need to write down iron 2 hydroxide. So iron 2 and a hydroxide. So that's -1. So again, the easiest way, think about this way. So this goes here and this goes here, which means I'll have iron. And that's going to be 1, but we don't put the 1 here. There's no subscript here. And I'll have OH. So that's going to be 2. And the 1 here that we don't show, so this will be the iron 2 hydroxide. Now, binary covalent compounds type 3. So type 3, these are going to be between 2 nonmetals. And essentially, it's all going to follow the same things that we learned, except here sometimes you'll need to add some prefixes such as mono, di, tri, tetra, and etc. For example, NO or N2O3. So how do you name this? If this was a metal, you would just say sodium oxide or something like that. You don't say how many of the atoms you have. But if it's non-metals, then you do need to mention it. So you're going to say that this is dinitrogen trioxide. as an example. A few exceptions that I'll go over here. So you don't use the mono. For example, if it's a CO2, so this is called carbon dioxide. That's what is being exhaled, right? So it's the gas that we exhale. So carbon monoxide, we're not saying that this is monocarbon dioxide. We're saying that this is just carbon dioxide. For the second element, we do mention how many we have, but not for the first one. And if it was CO, which is also from the, let's say, combustion gases, it's an incomplete combustion gases, and that's a toxic gas. So reading the textbook and search a little bit, you need to be careful when you're using your car. For example, you're in a cold state, you shouldn't start your car and be in the garage, because CO is very toxic and it cannot be sensed by humans. So now we're not saying that this is monocarbon monoxide, but we're saying that this is carbon monoxide, to emphasize that it is actually just one oxygen, but we don't use the mono for the first element. Other than that, it's going to be following the same rules as we discussed for the ionic compounds, using the prefixes. So you need to know these ones. If you have forgotten, go over and remember. So going from mono, di, tri, tetra, penta, etc. So all the way to 10, even though usually you would be going approximately up to 6. So some examples. CO2, we said already that this is the carbon dioxide. Now look at these molecules, try to name them. Right, so here we have 1 sulfur and we have 6 fluorine. So this is going to be sulfur hexafluoride. Here we have 2 nitrogens, so we do actually need to emphasize that we have 2 and we have 4 oxygens. So this is going to be dinitrogen tetroxide. And this is just a little summary of what we discussed together. So just go over it, and remember, the only thing here is that at the end your compound needs to have charge free. It needs to be charge free, so 0 charge. And other than that, simply follow the rules. If it's a metal, first type 1 metal, group 1 and 2, so keep the same name. If the charge can change, then you emphasize. If it's 2 or 3, with Roman numbers or by the prefix. And if it's non-metals together, then you're using a prefix, except for the first element, then for the one that you don't use the prefix mono. And then a little bit also about how to name the acids, and in general what acids are. So remember, acids are, this is a very common, very important class of chemicals in general, and they're common. So they, for example, the citruses that we're using, these are acidic. The vinegar is a acid, so the stomach juice is acidic. And the easiest way for you to recognize the acid is to look at the molecule and see that there is an H in the beginning. For example, HCl, that's an acid. H2SO4, that's an acid. HNO3, that is also an acid. And so 95% of the time, you're going to have the H in the beginning. So at least in General Chemistry 1, whenever you see an H in the beginning, remember that's an acid. That's just a general. And the properties that the acids have, first of all, they have corrosive properties. You can see here the statues get decomposed because of the acid rains. And this is all because the acids contain the H+, the proton, right? So this is called a proton. They're sources of protons. So what is the acid rain? So think about this, the exhaust gases, or the gases from the plants, so they evaporate, they go to the atmosphere. For example, SO2, NO2 or NO, they react with the humidity, with the water, and they're producing the acids in the atmosphere. And then these acids accumulate there, and then they're actually going to come down on us, and that's going to be called an acid rain. So fortunately, the acid rains are not concentrated enough. It's not a concentrated acidic solution, but over the year, for example, here, over, I don't know, 50, 100 years ago, you can see how it is actually changing and the constitution, so here, of the statue, so the concrete. So also in the batteries, the acid is used a lot. So this is actually concentrated acid, so just be careful. So as I mentioned, the source of the acid is going to be the H plus. This is what makes the acids, and usually it's going to be the first element that you can recognize. So for example, this is called the hydrochloric acid, even though sometimes one exception is the acetic acid, which you will see that the hydrogen may not be written in the beginning, but we will get to that. Let's go over naming the acids. So if it's a monoatomic ion, right? So if it's the one that ending with the "ide," for example, Cl minus, Br minus, and etc., then you're adding the prefix hydro. So H and Cl together, then I'm gonna say that this is called the hydrochloric acid. So changing the ending from "ide" to "ic, and we call these hydrochloric acid or hydrobromic acid, hydrosulfuric acid, and etc. So that's one type of the acids. So here we have it. So the hydrocyanic acid as well. And the second acid is going to be the ones that anion contain oxygen. So the most common ones, for example, SO4 2-, the most common anion, right, of the sulfur and the nitrogen and etc. So remember, these had the ending of 8. You had sulfate, nitrate, and etc. Now, when these become acid, first of all, SO4 2-, how many hydrogens do you think we should add? If I put 1, this is plus 1, then this is not going to be an accurate formula. I actually need to have H2SO4, right? So these are just going to have the ending of "ic." So that's the sulfuric acid. If I have HNO3, that's the nitric acid. I have H3PO4, that's the phosphoric acid. I have CH3COOH, that's called the acetic acid, because it is the acid of this ion. We have CH3COO negative, and that's called the acetate ion. So the acetate ion makes the acetic acid. Now, these can be written in different ways, so don't get confused. You can have C2H4O2 as well, but pay attention that the formula is the same. It always has the same number of the carbons and the hydrogens. So don't get confused whenever you see this. It's going to be the acetic acid. And also sometimes the H might be written in front, so it can be CH3O2, just to emphasize that it is an acid, even though this will be more like rare to see this. But yet again, just remember that this is all the acetic acid. So again, these are the acids of the common ions that have the ending of 8, and here there's no prefix or anything, so we're just changing it to "ic," right? So sulfuric, acetic, and etc. Right, so nitric, sulfuric, and acetic acids. So the ones that have less oxygen than the most common. So for example, HNO3, HNO2, H2SO3. This is from the nitrite, from the sulfite, from the chloride. Then now the ending is OUS, so nitrous, sulfurous, chlorous, and etc. So remember these combinations, how the ending of the acid comes depending on the types of the ions that we have. All right, so this is a little summary, a recap, so you can practice. Sodium chloride, going to bring the ions together, make sure that they're zero. Barium carbonate, so we have 2 plus and 2 minus, so together you need only one of each, BaCO3. So if the charge is not zero, then you just exchange these numbers. If the charge is not zero, then you exchange these numbers. The only exception that I remembered right now is you have H2O2, that's called hydrogen peroxide. So usually when you have 2 and 2, you would cancel, right? So let's say you had, suppose you need to make the formula of calcium sulfate. So it's going to be SO4, 2 plus, 2 minus. And let's say you follow this procedure and you cross them down here. So now you have 2SO4, 2. You did everything correct. But remember, whenever you have the same number, you're simply going to cancel them. If you cancel, no need for the parentheses anymore. So this is going to be just calcium sulfate. The only time that you wouldn't cancel them is going to be the hydrogen peroxide, because it is actually the formula. It is the way the atoms are connected here. So I have the hydrogen, oxygen, oxygen, and hydrogen. So don't cross them here. So it's one of the exceptions when the oxygen is -1 instead of -2, and this is still +1. These are the prefixes that we also discussed. Think about this for a moment. So which one do you think is named incorrectly? So the thing here is that all the formulas are correct. These are correct formulas. They do exist. This compound exists, but one of them is named incorrectly. Which one do you think is named incorrectly? Okay, so potassium nitrate. This is actually correct. This is the nitrate ion, potassium +1, group 1. The name is as it is, not changing. Titanium 2 oxide. What do you think? Is that correct? And how do you know if it's not correct or it is correct? So whenever you have a situation like this, try to start from something that is standard. And you know that oxygen is always going to be -2, except if it was a peroxide that we just talked about. So if this is -2 and you have 2 oxygens, then overall the oxygens bring a charge of -4. It means the counter ion, the titanium, actually needs to be +4, because that would be the only way to make it actually charge free 0. So this is not titanium 2 oxide, it is actually titanium 4 oxide. But other than that, thin 4 hydroxide, so this is actually correct because hydroxide has a -1. Therefore, the thin would have to be +4, so that you do 4 times 1. So overall, the hydroxide bring a -4 charge, and with 4 plus of the thin becomes a 0. Phosphorus pentabromide, that sounds good. The first element as it is, penta, prefix for 5 here, that sounds actually correct. Calcium chromate, it does actually sound correct because this is group 2, and if you don't know the chromate ion, if you look up in the table, you can see that this right here is the chromate ion. It has a charge of -2. So -2 combined with +2, that is actually correct. It is overall charge-free compound. These are related to organic molecules. You feel free to go over this as well. You will definitely need them in organic chemistry as well, but we won't cover this in general chemistry 1. Okay, so one more practice. Pause the video, try to put all of this here, and then we'll finish it together. But after that, you will need to do all the practices that you have from Blackboard. Zinc, nitrate. I'm gonna first put the ions and then I'll leave it to you to make sure that the final formula is correct. Carbon, dioxide. Well, this, I guess, not much to do, so it's already carbon dioxide. I have to have 2 here. Iron 2 chromate. It has to be +2 chromate. We have just seen in the previous slide that the chromate is -2. So think about that. Do we need to do anything here? Do we need to have 2 irons, 2 chromates, 3, or anything else? Cuprous sulfate. So first of all, sulfate, that should be easier. It's -2. Cuprous is an ion of copper, but OUS, it's the lower charge, and the copper can be +1 and +2. So in this case, it means that it actually is supposed to be +1. If it was +2, it will be cupric. Nitric acid. H, that's an acid. What is the nitric coming from? What ion is it coming from? NO3 minus, that's the most common oxy ion of the nitrogen. So I have NO3 minus, hydrogen here. 1 and 1, so this should be good enough. No need to change anything. Sodium acetate. Na, and the acetate ion CH3COO with a negative charge. Again, this can be written differently, so don't confuse it. 1 here, +1 here, -1 here. It's good as it is. Now let's go back here. So hopefully you figured out that zinc is 2+, looking in the chart. And so if this is 2+, this is -1, you need to cross these down, so you need to have 2 nitrate ions. And in order for them to be 2, you need to have a parenthesis to make sure that the 2 is referred to everything that is in the parenthesis. Carbon dioxide, it's good as it is. 2 and 2, good as it is. You would just need to write them a bit closer to make it look like just one formula. Cuprous sulfate, this is +1, 2. These 2 crosses down here, you need to have 2 coppers here, so this is going to be 2. And it is good as it is already with the 2. HNO3 is good, it's good as well. Now, one more thing that I'd like to mention, you do not have to have the charges all the time. In fact, most of the time in the textbook, you will see that people don't put the charges. We only do this in the beginning because we are just learning to write down formulas, but you might as well see a formula like this or a formula like this without showing the separate charges on the ions, and that is actually the common way how to say it. Now, the only thing is, do not confuse this when somebody asks you what's the formula of the iron 2 ion, right, or the ferrous ion. Well, in that case, if we are talking about the separate ion by itself, you do actually need to have the charge shown here. It must be shown here. But if it's already a compound, it's an ionic compound, then it's fine. You can go based on without showing the charges as well.